Good afternoon, my name is Wong Hong Hen. My matrix number is X6064 and I'm the student from the network computing. My supervisor is Ms. Nur Liana Binti Saladin and my examiner is Associate Professor Dr. Chiu Kan Len. And today I will be presenting my final year project 1, stock price movement prediction using LSTM networks. Introduction and background. The stock market is known for its volatility, which means that the prices can rise or fall rapidly due to many factors like economic events, market sentiment, or even unexpected global events. The traditional prediction models like ARIMA or SVM have been used for a long time, but they often struggle to capture these complex and non-linear patterns. This is where the deep learning comes in. The LSTM networks, which are a type of recurrent neural network, are designed to work with the sequential data. They can remember trends over time and learn temporal patterns in stock price movements. This capability makes the LSTM a powerful tool for predicting stock prices more accurately. It is very useful for investors who want to reduce the risk and make informed decisions. The problem statement for my project is the difficulty in predicting stock price movements. The stock prices are influenced by so many reasons such as economic events, news, and market sentiment. They fluctuate constantly, making accurate predictions challenging. For the traditional models, whether statistical like ARIMA or machine learning methods are limited because they often cannot capture the complex, nonlinear relationships in stock data. This means that the investor don't have a reliable tool to base their decisions on. This will increase the risk of financial loss. Therefore, the goal is to find a method that can learn patterns from historical stock data, account for temporal dependency, and make more accurate predictions for the future price movements. Especially the LSTM networks are suitable for this because they are designed to handle sequential data and remember trends over time. Moving on to objective and scope. The main objectives of my project is to develop a predictive model using LSTM networks to forecast the stock price movements. Second is to want to evaluate how well this model performs using historical stock data. Third is to compare its performance with traditional models to see if it actually provides the better accuracy. For the scope, this project focuses specifically on daily stock price data from selected companies or market indices. It is limited to predicting short-term movements rather than long-term trends. For the model development and testing, I use Python along with deep learning frameworks like TensorFlow or Keras. This will keep the project focused while still showing the capability of LSTM in real-world stock prediction. In the literature review, I organized past research into 4 main categories. First is the traditional statistical model like ARIMA and GARCH were some of the earliest approaches. They are very useful for linear time series forecasting but struggle with complex patterns. Second is the machine learning models such as SVM and ANN improved prediction accuracy by capturing the nonlinear relationships in the data. Third is the deep learning approaches, such as RNN and LSTM. These introduce memory mechanisms that allow the model to remember sequential information. This is very important for stock prices, since the past trends can influence the future movements. Finally is the recent trends involve hybrid and more advanced deep learning models. These approaches combine multiple techniques or add enhancements to improve the prediction accuracy even further. This evolution shows why LSTM is suitable for my project. This slide summarizes the main limitation of different models used for stock prediction from 2000 to 2025. From 2000 to 2005, traditional models like ARIMA, linear regression, and GARCH were commonly used. Their main limitations were their linear assumptions. They cannot handle nonlinear patterns well and there are lack of long-term memory, which causing them ineffective at capturing sudden market volatility. Between 2005 and 2015 is the machine learning models like SVM, ANN, and random forest. These models improve nonlinear prediction, but they still treated each data point independently. They did not have sequential learning capabilities and often required heavy feature engineering. From 2015 to 2020, deep learning models like RNN and LSTM were introduced. RNN had problems with vanishing gradients and unstable training, while LSTM were more capable but heavier to train and needed the larger datasets. Finally, in the period of 2020 and 2025, advanced models like transformers, hybrid CNN, LSTM, GRU, and reinforcement learning models emerged. While they provide higher prediction accuracy, they also demand very large datasets, high computational resources, complex hyperparameter tuning, and they risk overfitting on smaller financial datasets. This progression shows how models have evolved, but also highlights the trade-off we face between accuracy and practicality, which is why LSTM is a good choice for this project because it balances the sequential learning with manageable complexity. Moving on to the methodology. This figure shows the overall methodology of my project. It starts with the collecting historical stock price data from selected companies or indices. Then the data is pre-processed, like cleaned, normalized, and converted into sequences using the sliding window approach, which is essential for training the LSTM. Next, the LSTM model is designed with input layers, LSTM layers to capture the temporal dependencies, dropout layers to prevent overfitting, and output layer for predictions. The model is then trained using historical data with the Adam optimizer and mean square error as the loss function. Finally, the model is evaluated on unseen data to measure the performance using matrices like RMSE and accuracy. Using this workflow ensures that the model can learn from past trends and make the reliable predictions for future stock price movements. Data pre-processing is an important step in my project because the quality and the format of the data is directly affect the model's performance. First, I perform the data cleaning. This means that removing the missing, inconsistent, or duplicated values to ensure the dataset is reliable. Next, I normalize the data using the minimum-maximum scaling. This transforms all the stock prices and features into a consistent range between 0 and 1. Normalization is important because LSTM models perform better when input values are on a similar scale. After that, I apply the sliding window technique. This converts the continuous stock price series into the sequences that the LSTM can process. For example, the model can look at the last n days of prices to predict the next day's movements. Finally, I select relevant features such as open, close, high, low, and volume, which are important indicators for stock price movements. Overall, these steps prepare the data to the LSTM model can learn effectively from historical stock trends. Here is the architecture of the LSTM model used in my project. The input layer takes sequences of stock prices and other selected features such as open, close, high, low, and volume. These sequences come from the sliding window pre-processing step. The LSTM layers are the core of the model. They are capable of remembering patterns over time, which allows the model to learn temporal dependencies in stock price movements. A dropout layer is added to prevent the overfitting. This works by randomly ignoring some neurons during training, which forces the model to generalize better. Finally, the dense output layer generates the predicted stock price movement. This architecture ensures that the model can effectively learn from the historical sequences and make the accurate predictions for the next time step. After designing the LSTM model, the next step is training. For the model training procedure, I use the Adam optimizer because it efficiently adjusts the network weights to minimize the errors. The loss function I use is mean square error, which calculates the difference between the predicted and actual stock prices. Minimizing MSE helps the model make more accurate predictions. Hyperparameters play an important role in training. Epochs determine how many times the model sees the entire training dataset, while the batch size controls how many samples are processed before the model updates its weights. Choosing the right values is important to balance the learning speed and the accuracy. During the training, I also monitor both training and validation loss. This helps to ensure the model is learning general patterns from the data rather than just overfitting to the training set. By carefully training the model with these settings, we can achieve reliable predictions on unseen stock data. Once the model generates predictions, I evaluate its performance using three matrices. First is mean absolute error, calculates the average absolute difference between the predicted and actual stock prices, causing it easy to interpret in the same units as the stock prices. Second is the root mean square error, emphasize the larger errors, which helps highlight the significant deviations. And the third one is the coefficient of determinations, R-squared, measures how well the model explains the variance in the actual stock prices. A value close to 1 indicates the high predictive accuracy. By using all three metrics together gives a comprehensive assessment of the LSTM model's predictive capability. The expected outcomes of this project are focused on how well the LSTM model can predict the stock prices and provide the useful insights. First, the model is expected to deliver accurate predictions, meaning that the predicted stock prices should be closely matched to the actual prices. This will be reflected in low MAE and RMSE values, showing that the prediction errors are minimal. In addition to accuracy, the model should demonstrate high reliability. A strong R-squared score would indicate that the model can effectively explain the variability in historical stock prices, which is important for dependable forecasting. Another key expectation is that the model can capture temporal patterns in the stock data. By learning from sequential dependency over time, the LSTM can identify trends and patterns that improve the quality of future predictions. The model is also expected to provide the practical insights for investor and financial analysis. This insight can help the user to make more informed financial decisions and manage the potential risks based on the predicted stock movements. Finally, this work serves as a foundation for future improvements. The current model and methodology can be extended with hybrid architectures, additional features, or even larger datasets to enhance the predictive performance and explore more advanced applications in stock prediction. In conclusion, this project shows that LSTM-based model can effectively predict stock price movements by using the historical data. The use of regression-based evaluation metrics such as MAE, RMSE, and R-squared provides assessment of the model's predictive accuracy. The LSTM model is particularly capable of capturing the temporal dependency within the stock data, allowing it to recognize the sequential trends and patterns, which enhance its prediction performance. Based on the expected outcomes, this approach has the potential to improve the valuable insight for investors and financial analysts in making informed decisions. Finally, this work lays a solid foundation for future research where the model could be further improved with hybrid approaches, additional datasets, or more advanced architectures to achieve even better prediction results. And that is all from me. Thank you.